So what I want to do is let's first draw a picture here. And I want to find the work done by a 10-pound force, okay, acting in the direction 1, 2. So if we were referring back to Braden moving the box, that would be the angle at which he was pulling with which, and then the angle where the object was moving, okay? So the 1, 2 is describing his vector, therefore we're going to have to use some of our formula sheet to find that angle. We are moving the object 3 feet, and we're going to just put those 3 feet on the x-axis. So here's my object. We're moving it along the x-axis 3 feet. This is the vector that's pulling, okay, and that vector has components 1 and 2. Okay. So in order to do this, now I give you the force. I give you the 10-pound force. That's my F. Did I give you the angle? I didn't, but I can find it out. Did I give you the distance? Yes. Okay. So how are we going to figure out what theta is? Oh, we know how to do that. We've done that before. Okay. We can find the angle between the x-axis and a vector by taking the tan inverse of the vertical divided by the horizontal. All right, would you do that, please? What do we got? 60 what? Okay, I'll call it 63.4 degrees. Okay. And then, gosh, when they're doing in physics, what label do they use for work usually? Do you remember? It's not what I'm going to use. I'm going to use something called foot-pounds, and 1 foot-pound would be the work required to move 1 pound 1 foot. Okay. In physics, they don't use foot-pounds. We can look it up at the end. I can't remember what the units they use, but all right. So we're going to take the force, which was 10 pounds. The cosine of the angle. Let me tell you why we're taking the cosine of the angle a second. And then times the distance. Okay. So do you see this vector here that's pulling the object, but is that the direction the object's going? We have to figure out what part of the force is pulling it that way. So essentially what we just did is we found this right here is just the horizontal component, the part that's moving it directly to the right. Okay. All right. Let's calculate that. I got 13.4. Do you get the same thing? Okay. All right, so next, what if, does it make sense? Hopefully. What if I had a force of 30 pounds acting in the direction 2, 2, and this time we're moving an object 3 feet from 0, 0, to a point in the first quadrant along the line y equals 0.5x. So this time I am not moving it in the same way. Okay, so here's what we're going to do. Let's draw a picture always. Let's go ahead and just put 5 tick marks on our x and y axis. The first thing I'm going to do is I'm going to draw the force vector, and the force vector is at 2, 2. So the force vector is like that. Okay. Now, unlike the last example though, we are not dragging the object straight to the right, we're dragging it up an incline. And sometimes I'll give you the degree of the incline, but just for the heck of it, I did not. I gave you the equation for a line. So the key thing here is, what is the slope of this line? I wanted to answer quicker than that. What's the slope of this line? 0.5, okay? Okay, right? This line. Right there, 0.5. So I'm going to draw a line that starts at 0, 0 and has a slope of 0.5. 0.5 is 1/2, agreed? So can't I go up 1 over 2? Okay, so if I went up 1 over 2, that would be right here. I'm going to do it again. Okay. So, the object is going to be moving 3 feet along this line. When we're calculating the work formula, what we need is the angle between the force and how the object is moving. So no longer is that angle this entire angle, but theta now is the angle that's in here. So put theta in there. I need to figure out that little theta, and I'm going to be able to do it. Okay, here's what I'm going to tell you. If I would take the 2, 2 vector, I'm going to draw this. Okay, I'm going to call the angle between the x-axis and 2, 2 theta 1. Okay, and then I'm going to call the angle between the x-axis and the line theta 2. How could I find this little angle from theta 1 and theta 2? Yeah, theta 1 minus theta 2 would equal theta. Okay. Let's find theta 1. Theta 1, we're going to take the tan inverse of 2 over 2. Some of you, without even doing any math, know what that angle is already. 2, 2 is halfway through the quadrant, right? What's the measure of that angle then? 45. But if, let's say it was a different vector, then you would have to find it. Okay, how am I going to find the coordinates of theta 2? Yeah, let's just think of it as a vector again. Remember, we went up 1 over 2. Okay, if we're going up 1 that over 2, isn't this the same as the vector 2, 1? Yes? All right, so I'm going to take tan inverse of 1/2 to find theta 2. Can you do that for me? I'll do that. Okay, just a side note, because I like to just give you as much knowledge as possible. If you ever wanted to find the angle of a line, if you had its slope, it's just the tan inverse of its slope, because the tangent is the opposite over the adjacent. Okay, and the slope is the rise over the run. Those are the same thing. So if you ever have an equation for a line going through the origin, and you wanted to figure out what the angle the line made with the x-axis, it's always the tan inverse of its slope. Just a little tidbit of information. All right, so what's this little angle then? Well, let's subtract these two. What's 45 take away 26.6? Okay. And that looks kind of accurate because that's a pretty little angle. All right, so now we have the 3 things we need to find the work done. So the work equals the force. The force required to move the object was 30 pounds. The angle between the object moving and the direction vector is 18.4. So we're going to take cosine of 18.4. And the distance is 3. Okay, I got 85.4. Is that what you got? What our book does is they use what they call vector projections. They project vectors and move them. So what they would do is they project this like little angle, and they move it down to the x-axis. And I just think that's too hard. My brain doesn't work that way, so I don't teach it that way. Foot-pounds. All right. Actually, example 3 should be more like before this. This isn't work done. This is just asking about a force. It was Aunt Becky, but okay. You don't know Aunt Becky.
I do.
I know you do, Jim. You're the only one. All right, so all this, we're not talking about work, we're just talking about how, this isn't work done because we're not moving an object, but we're talking about a force that would hold something up, okay? So let's say Becky is sitting on a sled at the side of a hill at an incline of 30 degrees. So let's try to draw a 30-degree angle. This is like our hill. And kind of towards the top of this, we're going to draw like a sled. Oh boy. And a person sitting on a sled. You can tell that. Yes. I was a wonderful art student. Just kidding. All right, so the combined weight of Becky and the sled is 130 pounds. Okay, so this is a key thing. This is a force. The combined weight of something, even if it's on the hill, would go straight down to the ground. So what we're going to do is we're going to draw an arrow straight down to the ground with it. It is going to be a triangle, Drew. And we're going to put a 130 there because there is a force, a weight that's pulling it down. Now, this is where it gets a little, if you're not a good drawer, it might get a little tricky. What I want you to do then, because we need to figure out this little here, what's the force that's holding her up on that hill? This needs to be part of our triangle. So what I want you to do is connect this with a right angle. So make that a right angle right there. And if you need to, you might have to extend the force down. Okay, this is how you set up all of these problems. We are trying to figure out this force right here, the force on an angle that's holding Becky up and not letting her slide down the hill. Where does the 30 come into play? Well, this 30 right here, think this whole right angle. If this is 30 right here, what's the angle at the top? 60. Also, this 30 right here would then be the same as this angle right here. So this is 30. All right, so ignoring the big triangle, now look at the little triangle that we just drew. Remember, I'm trying to figure out this force, which I'm going to represent with the length of this piece. What are some, think SOHCAHTOA, what are some ways you could find F? Give me one way. Use this little triangle. Just think SOHCAHTOA. This is a triangle. How could you find F from the information? Give me one way. Okay, hold on. This isn't adjacent though. What piece is this? That's the hypotenuse. We're looking at the little triangle. So sine with what angle, Mason?
30.
So he's saying you could use sine of 30 equals opposite over adjacent. What else could you do?
60.
If you use 60, you'd use cosine. Either of those works. Okay, let's figure it out. Let's see. If you're in these two sets of desks, would you use the sine 30 expression? if you're in those two sets of desks, you're going to use the cosine 60 expression. We're just confirming that we get the same thing. Okay. Did you get 65?
Yeah.
All right. So 65 pounds would be the force required to keep that sled from sliding down the hill. Okay, because part of that weight of them holding them down is doing part of that work for you. Okay, but part of it's gonna, it has to come from the side to hold it up. Is that all you have to do? Yeah.